of the Jones polynomial was the sort of second polynomial invariant of knots. It came something like 60 or 70 years after the Alexander polynomial, but it has an elementary definition in terms of the Kaufman bracket. It's completely diagrammatic. So you associate the following polynomial to a knot diagram. If it's just got a single unknotted circle, you say that's 1. If you have an unknotted circle that's disjoint from and unlinked from some other diagram, then you can remove that circle and pick up a factor of some variable minus a squared minus a to the negative 2. And then there's a skein relation that locally, if your diagram has a crossing that looks like this, you can break it up into a sum of Kaufman brackets of the resolutions at the two resolutions at that crossing that give you something crossingless. So there's a times this sort of vertical resolution plus a minus times this horizontal resolution. And so that gives you, that's actually an invariant of a framed knot. To get the Jones polynomial, you normalize by some factor. You take the Kaufman bracket of the knot diagram you're given, and then you substitute Q equals some function of A. And that's an invariant of the knot. And so simple questions we don't know about it after 30 something years. Does it detect the unknot? In other words, is there a knot other than the unknot, which has the same Jones polynomial as the unknot, namely 1? We also don't know, does it detect the trefoils, the left or right-handed ones? Does it tell them apart from other knots? Or even the figure 8 knot? We just don't know about any of these. On the other hand, if you look at the standard, say, Rolfson knot tables, the next one, we do know the answer. It doesn't detect the cinquefoil, the 2-5 torus knot, which looks like this. This is its Jones polynomial. You can take my word for it if you want, look it up on the knot atlas. It's the same Jones polynomial as the knot 10-132. So it's definitely not a complete knot invariant. Now, as for how you might evaluate it, well, we had this relation for the Kaufman bracket where you replace a crossing with 2 different Kaufman brackets of diagrams that have 1 fewer crossing. And the other axioms included, well, if you have a diagram that's just n unknots that are unlinked from each other, we know the value of the Kaufman bracket, then that lets you compute this as what's called a state sum. So this is a picture. Barnaton wrote a really nice expository paper about how to compute Khovanov homology back when it was new. And so this is his picture of how you do it for this diagram of the trefoil. You say, well, I've got 1, 2, 3 crossings. And at each crossing, you pick one of 2 resolutions. You get some union of circles. For example, here, you've resolved all 3 crossings and you're left with 2 circles. So you associate Q plus Q inverse squared to that. And you've got 2 to the 3rd power resolutions that leave you with no crossing. So you do all 8 of them organized in this hypercube. Each of them gives you some polynomial and you just add them all up. And that's how you might evaluate the Jones polynomial. Now, the reason I show this picture from a paper on Khovanov homology is that this sort of leads naturally to the construction of Khovanov homology. This is a knot invariant that, it's a categorification. It replaces a polynomial with a bigraded vector space or bigraded group if you prefer. The idea is you take exactly that same picture and replace polynomials with chain complexes in which each sort of summand has graded dimension, whatever that polynomial was. So anytime you have a factor like Q plus Q inverse, you take a 2-dimensional graded vector space with one generator in degree 1 and another in degree -1. So here's essentially the same picture for the trefoil. You do the same cube of resolutions as it's called, but now you've got, instead of polynomials, you've got these tensor products and shifted vector spaces with shifted grading and so on. And these edges that were just sort of there to suggest a hypercube before, now you replace them with arrows, maps between those vector spaces. You get a chain complex. This is Barnaton's illustration of it from the same paper. And the homology of that is a knot invariant. And like I said, it categorifies the Jones polynomial. So it's a functor from a category of links and link cobordisms to bigraded vector spaces. But the Jones polynomial specifically appears as the graded Euler characteristic of it. So you take among the 2 gradings it's equipped with, you sort of collapse one of them and preserve the other. And when you do that, you get the Jones polynomial back. So since it has at least as much information, you could ask the hopefully easier question of, does it detect the unknot or really anything else? And now that we have a homology theory, we have extra structure. In particular, this cube of resolutions just very naturally gives you an exact triangle that says if you have a knot, like with a local picture like this, some crossing oriented that way, you can do either of the two resolutions of that crossing and you get a short exact sequence. And this just falls out because, you know, the complex for this term is half the cube of resolutions. The complex for this term is the other half. So you're really just seeing the Khovanov homology of the knot as, or the link as a mapping cone. And this has a lot of familiar counterparts, short exact sequences in Floer theory leading to spectral sequences. So a typical example, the first one that we had due to Ojvath and Sabo in 2003, goes from the Khovanov homology of a link to the simplest version, the hat version of Heegard-Floer homology of the branch double cover of that link. And technically with the, we have to reverse orientation. We take the mirror of the link. Similarly, in about 2010, Kronheimer and Ruvka constructed a homology theory for knots called singular instanton knot homology. And there's a spectral sequence from Khovanov homology to that. That's isomorphic to something more geometric called instanton knot homology. So I just put that in there in case that might be more familiar. And then in 2018, Nate Dallin found a spectral sequence from a Khovanov homology to, in fact, knot Floer homology, which is sort of strictly better than the first one because knot Floer homology somehow has more information than it's bigger generally than the Heegard-Floer homology, the branch double cover. And so we can apply all of these to this question about detecting the unknot or anything else because spectral sequences give you rank inequalities. So the strategy so far, if you want to prove that Khovanov homology detects a knot, you do the following. You use these spectral sequences, either the one by Kronheimer and Ruvka or the one by Dallin, to bound the Floer homology of K, by which I mean not Floer homology, instanton knot homology, one of these invariants. Using those bounds, you show that K has to be a fibered knot and that its cipher genus has to be at most one. And so if you're working with Heegard-Floer homology, that's Paolo's result. If you're working with instanton knot homology, Kronheimer and Ruvka proved that building on Paolo and lots of other people. And once you know this, you're essentially done because there aren't that many fibered knots of genus at most one. K has to be either the unknot. So Kronheimer and Ruvka proved that Khovanov homology does distinguish the unknot from everything else. Or it could be a trefoil. So Baldwin and I a few years ago used the strategy to prove that it distinguishes the trefoils from everything else. Or it could be the figure 8. And once Dallin's spectral sequence came out, this was proved relatively quickly by Baldwin, Dallin, Levine, Lindman, and Sesdanovich. But that's sort of the end of this strategy because we're out of fibered genus 1 knots or genus 0 knots. So you might say, well, I could at least try and do the first 1.5 steps down the Floer homology of a given knot, show that it's fibered and maybe the genus is bigger than that. But the problem is that for genus 2 and any higher genus than that, there are infinitely many fibered knots. So this strategy is kind of hopeless, at least, you know, as I've stated it here. But the main goal of this talk is to sort of ignore that trouble and you know, break through this barrier. And so this theorem that I proved with Baldwin and Hu says that if you have a knot whose Khovanov homology with coefficients in Z mod 2 is the same as that of the 2,5 torus knot pictured over here, then K has to actually be isotopic to the 2,5 torus knot. So that's the goal of this talk. And I should say, maybe just as a word of warning, that I know this is a symplectic geometry seminar and sort of nothing I've said so far is really symplectic. And you know, I apologize for that. I've tried to sort of shoehorn some content in, so we're at least a little bit happy about it, because there are symplectic versions of Khovanov homology and so on. So as a remark along those lines, there's a symplectic version of Khovanov homology due to Seidel and Smith. What you do is you take your knot, you represent it as the closure of an M-stranded braid. Then you say, I'm going to build some interesting Stein manifold. What you do is you look at the adjoint action on SL2M. You take a transverse slice to that action centered at some nilpotent matrix with 2 Jordan blocks of size M. And then you construct a braid group action on that slice. So you know, we have that action, you find sort of an interesting Lagrangian in there. And then the symplectic Khovanov homology, as it's called, is just the Lagrangian Floer homology of that L with, you know, the thing you get by acting on L by your braid. And so Seidel and Smith proved that this doesn't depend on the particular braid you use to represent your knot. So you get an invariant. And actually, not that long ago, Buzite and Smith proved that this is isomorphic to the original Khovanov homology, at least over a field of characteristic 0, which is, you know, I mean, it's great, but it, you know, what I'm talking about, unfortunately, doesn't say much about that because we only have this proof over a field of characteristic 2. So it's still open, in fact. I mean, it's probably true. How could it not be true? But it's still open whether symplectic Khovanov homology does detect the 2,5 torus knot. For everything leading up to this, for the unknot, the trefoils, and the figure 8, those results all held over the rational numbers. And so we know that symplectic Khovanov homology does detect those as well. But we'll see later on that the reason for these, having to work with coefficients mod 2 is that we're gonna have to apply Smith theory to something with an action of order 2 in involution. And so we're stuck with these coefficients. That's life. But anyway, that's the main theorem. And so here's the strategy of the proof. This is the goal. The first thing we're going to do is return to Floer homology of knots and show that if K has the same Khovanov homology as the 2,5 torus knot, then it also has the same knot Floer homology. And knot Floer homology detects fiberness. This is now a result of Gigini and Ni, because we need to use work of Ni to get to genus 2 and up. Once we do that, our knot is fibered. The complement fibers over the circle. So we'll study the monodromy of that fibration, and that's where periodic Floer homology comes in. So this was a cousin of embedded contact homology that sort of counts fixed points of a surface or other homeomorphism. Using this, we're going to realize the knot complement as the branch double cover of some 5 braid. So the braid sits in a solid torus, and we're going to say we take the branch double cover over the closure of that braid, and we're going to realize our knot complement that way. And once we've done that, now we sort of switch to Khovanov homology and use some deep structure about, like I said, Smith inequalities and so on, to show that braid has to be also, that braid is braided about its axis, but the converse is true. The axis is braided about that braid as well. And I'll show pictures of this later, but that's a very strong restriction. That gets us to the point where you can do a computer search and conclude the theorem. So that's the goal. That I'm going to try and get through all 5 of these in the time we've got. Any questions before I move on?
Yes, so you mean the proof is using computer assistance for this?
Yes. Yeah, it's this last step here uses a bunch of code written in Sage, which also involves SnapP and all of it. If you read the SnapP documentation, they say that it does verified computations if it tells you a result is true, that they've proved it, and that may not be up to lean standards, but in principle, you could, in principle, this whole thing might be verifiable. Well, except for this part, which requires hundreds of pages of work of Lee and Taubes, but
when
this part
means verified, I mean they use interval arithmetic. It doesn't mean the proof is checked. It means that the numerical analysis is
right. Well, my understanding is that when SnapP says that 2 manifolds are isometric, it has actually found an isometry between them. But you're right; it uses interval arithmetic. But there are some theorems about how small an interval do you need to certify in order to know that there actually exists an isometry. That's my understanding. I mean, Mark Kohler or Nathan Dunfield would be a better person to ask, but I believe they actually do mean that it really is certified to the extent that Sage can certify anything.
Yeah, exactly. To the extent that Sage certify anything.
I don't mean that as a shortcoming. I just mean you have to accept that Sage is correct. But I think if it says the computation returns true, then it actually is true. I think. Anyway, it would probably be possible without sort of numerical computations as well, but we just didn't do that.
That's fine.
All right. So I want to start with step 1. The understanding the monodromy of a knot that has the Khovanov homology of this 2,5 torus knot. And the proposition that I claimed in step 1 was that it has the same knot Floer homology as well as the 2,5 torus knot, if their Khovanov homologies agree. This is over here, a figure just plotted on the in 2 dimensions of the the Khovanov homology of the 2,5 torus knot, in case, I should put that somewhere. So it's, these are supposed to be copies of the field of two elements in each of these bigradings along a single diagonal. All right, so the very quick outline of the proof is that the universal coefficient theorem says that the dimension over the rationals is less than or equal to the dimension over the field of two elements, which looking over here is 5. We know the left side can't be 1 because Kronheimer and Rivka proved that it would be the unknot. We know that it can't be 3 because Baldwin and I proved that it would be the trefoil. So it has to actually be 5. And what that says, looking back at the universal coefficient theorem, is that over the rationals, it's supported in exactly the same set of bigradings as it is over Z mod 2. And so now we apply this Dallin spectral sequence from Khovanov homology to knot Floer homology to conclude that the knot Floer homology had to be what we claimed it was. So the goal, at least for the first part of the talk, is to see what that tells us, knowing this knot Floer homology. All right, so I've just restated that proposition up here so we can remember that we're supposed to know it. So a couple things we can read off of the knot Floer homology are whether or not it's fibered, which it is, the Seifert genus, which is 2, and the Alexander polynomial. And we know enough about Alexander polynomials to say that there can't be a fibered satellite knot of genus 2 that has that Alexander polynomial. There also can't be any torus knot other than T25. So the knot is actually hyperbolic. And so I've drawn it here as the mapping torus of some diffeomorphism of a punctured genus 2 surface. Let's call it H. Now, when you have a fibered manifold that's hyperbolic, we know that the monodromy has to be pseudo-Anosov. And so we can start to talk about the dynamics. All right, so the proposition is that H, our monodromy, is freely isotopic. You're allowed to rotate the boundary if you want, to a pseudo-Anosov map, and that map has no fixed points. And this is where we really start to use sort of deep input from Floer theory. Well, even deeper, I should say. So the idea is to show that if we do zero surgery, longitudinal surgery on the knot, then we get a bundle of closed surfaces over the circle. So it fibers over the circle, and the monodromy looks the same after we fill in that puncture, the puncture from back here. So what we want to do is compute really a nice version of the Hegardt-Floer homology of that zero surgery, that closed 3 manifold, using the knot Floer homology, and then relate that, I guess I'm going to go from right to left here, relate the Hegardt-Floer homology to the monopole Floer homology of the same manifold, which we can then relate to the periodic Floer homology of the monodromy. And I put a little hat here to indicate that we filled it in. So using that, we'll actually just determine the periodic Floer homology of this map. And so these isomorphisms, because I should give people credit for probably 1,000 pages of work or something, is Lee and Taubes proved that periodic Floer homology looks like monopole Floer homology. And then several teams of people related that to HF+. There's Kutlahan, Lee, and Taubes, and there's also Kolan, Gagini, and Honda, if maybe you add in work of Taubes as well. But there's sort of, there's a lot hiding in these isomorphisms. And the point is that, well, just a very small portion of the periodic Floer homology is really the symplectic Floer homology as studied by Seidel and others of that monodromy of this closed genus 2 surface. There's a problem though, which is really unfortunate, is that, so when I write PFH sub 1, I mean that periodic Floer homology is generated by fixed points or by periodic points of this map H, and we're just looking at the part generated by fixed points. And invoking this isomorphism here, well, there's some monotonicity condition that actually requires the genus to be at least 2. And we're in the case where it's actually 2. So, you sort of throw your hands up at this point and say, what am I supposed to do? But there's a trick, which is to replace our knot K with a different knot. We take the connect sum of K with its mirror image. So there's K and I draw like its mirror image backwards. You just sort of tube them together and you get a new knot. And this is still a fibered knot. If you do the zero surgery, you get a 3 manifold that fibers over the circle. And now the monodromy, the fiber is a genus 4 surface. You take the 2 punctured genus 2 surfaces corresponding to K and its mirror, and you just sort of glue them together. you apply H, our monodromy on one side, and you apply, I guess, the inverse of H on the other side. And that's the monodromy of this manifold. And now things are good because we're actually on a genus 4 surface. So this monotonicity that Lie and Taubes require is now satisfied. There's a Kuhneth formula for knot-Floer homology that lets us compute the knot-Floer homology of this connected sum. And so we go through the same strategy. We compute the Heggard-Floer homology of the surgery, which is entirely standard. And the upshot is that after we've gone through all these isomorphisms, the symplectic Floer homology of this genus 4 diffeomorphism actually vanishes. It's 0. Okay, so now we have to understand that computation. Like, what does it actually mean? Well, the chain complex for symplectic Floer homology is generated, again, by fixed points of F. And you can think of these as being generated by sections of the mapping torus. So, you take the mapping torus of F and you just say, well, you have a section corresponding to any fixed point. If you have like a period 2 point, you might have a multi-section where you wrap around the circle direction twice and so on. But really, we're just looking at these sort of very natural sections. And the differential on the symplectic Floer chain complex, if we look at the matrix coefficient for, say, a pair of fixed points, it counts J holomorphic cylinders in R times the mapping torus. The mapping torus has a natural stable Hamiltonian structure, so you go through the whole usual setup, and you want the cylinders to be asymptotic at infinity to alpha at one end and beta at the other, whatever these fixed points are. Now, in his thesis, Andy Cotton Clay did a complete computation of symplectic Floer homology for any mapping class that isn't periodic. In other words, some power of it isn't isotopic to the identity. And that's the situation we're in here. So the simplest version is when you have a pseudo-Anosov map. This is sort of the generic case. This is the case we wanted to be in, but the monotonicity condition failed. And it's known just by general facts about surface diffeomorphisms that if you have a pseudo-Anosov map, no two of these sections, alpha and beta, that correspond to fixed points are homotopic. They're said to be in different Nielsen classes. And since they can't be homotopic, there can't possibly be a J holomorphic cylinder in R times mapping torus, because it would project down to a homotopy. So that says the differential has to vanish and just identically. Now, we're not in that case. We're in the so-called reducible case where there's a curve that's fixed. So just to draw schematically, here's my genus 4 surface. This curve in the middle that we got by gluing our surfaces together is supposed to be fixed by the monodromy. So this is actually a reducible mapping class that we're studying. And in that case, the decomposition is more complicated, but you decompose your surface into pieces so that it's pseudo-Anosov or periodic on each of them with some extra hypotheses. And then there's a nice decomposition of the symplectic Floer homology. And in particular, for each of the pseudo-Anosov components, the chain complex associated to that component is a summand of the eventual homology, because it would be HF symplectic, but the differential is 0. So you can just think of it as the chain complex. And so if we know that the symplectic homology of this reducible mapping class is 0, well, H is supposed to be pseudo-Anosov, H inverse is also pseudo-Anosov. So by this second bullet point here, the symplectic Floer homology of the pseudo-Anosov that in the same mapping class as H, that vanishes because it's a summand of 0. And since it vanishes, sorry?
I'm a bit confused.
Yep.
If you are reducible, you have this curve which is fixed. Shouldn't this produce two generators?
It's complicated. We spent a while trying to sort this out and eventually just emailed Andy Cotton Clay and said, what's going on here? And the point is that we're gluing together a pair of maps which are not themselves pseudo-Anosov. They're freely isotopic to pseudo-Anosovs. And that free isotopy rotates the boundary by some amount. And depending on what that rotation is, you might find extra generators corresponding to that curve in the middle. It sort of depends on like how many total twists you do on each side. So, it is possible that you could get something non-zero if you glue together two pseudo-Anosovs where there are no fixed points. But here, the point of using H and its inverse is that these rotations sort of cancel out. And so there's no fixed points left. The description in Cotton Clay's paper is sort of it's very, very hard to pick this out. But the point being that when you do this rotation, you get some number of regions in between where you might say like, it's, you know, periodic or it's a Dane twist on each region, on each cylinder or something, but you're only allowed one Dane twist per region. And so you might have to have a whole bunch of these next to each other if there's a lot of twisting. And that might contribute a lot to the rank. But again, here, because these rotations cancel out, there's just nothing left. So I don't know if that answered your question, but
yes.
I guess, the point is, you know, it's possible for there to be zero from that reducible curve, but it's possible for there to be more as well. So is that all right?
Yeah. All
right, great. So we've shown that the monodromy of this knot, that again had the same knot Floer homology as T25, well, its symplectic Floer chain complex is 0. That means it has no fixed points. And so once we know this, you know, we've sort of taken this detour from Khovanov homology through a couple different types of Floer homology, and that's told us something non-trivial about the dynamics of the monodromy of this knot. Okay, so what does it mean? Now we know it's freely isotopic to the pseudo-Anosov. Well, it means, this is just recalling what a pseudo-Anosov map is, that there's a pair of measured singular foliations on the surface. So you have a foliation and you have a transverse measure, and there's two of these, so that if you apply the pseudo-Anosov map, it takes the so-called stable foliation and contracts it by some factor lambda, and it takes the so-called unstable foliation and expands it by that same factor lambda. Lambda is some real number bigger than 1. It's called the dilatation of that mapping class. And these foliations are supposed to be transverse to each other, except at the singularities. At the singularities, we have these so-called n-pronged saddles, where, so I've drawn, you know, one foliation in red and one in blue. Here's a 3-pronged singularity, because the red foliation has, well, 3 sort of leaves coming into that singularity, and the blue one does as well. So you could have 3 prongs, 4, 5, you could, you know, any number, at least 3. If you have 2, it's not a singularity. So you have to have at least 3. You can have fewer prongs on the boundary if your surface has boundary, but you know, there has to be at least 1 prong on the boundary. Okay, and if that's the case, then we know if that number is m, then the isotopy from our monodromy to this actual pseudo-Anosov map ends up rotating the boundary of the surface by some fractional number of rotations. That's called the fractional Dane twist coefficient of this map H. And we know that this H has to be some integral multiple of 1 over m, 1 over the number of boundary prongs. Now, another thing we can deduce from knowing the knot Floer homology matches that of T25 is that K is strongly quasi-positive. This has a couple definitions, but my preferred one is that given that it's fibered, that the open book decomposition of S3 induced by this fibration supports the tight contact structure on S3. And if you know it's strongly quasi-positive, then you can show actually that the fractional Dane twist coefficient is strictly between 0 and 1, but it has to be a multiple of 1 over m, and so m has to be at least 2. All right, so you've got some foliation, a pair of singular foliations on your surface, and on the boundary, maybe I should just draw a very quick picture. So like if there's a boundary puncture like that, you have to have at least 2 prongs. You could have 1 and then it would just wrap around, it would just curl around the puncture like that. But there have to be at least 2. And if there's exactly 2, then the foliation might look something like this in a neighborhood of the puncture. Okay, so that's more information about the dynamics that we've managed to extract. Now here's a proposition that follows from this. We're trying to reduce the problem, I guess, back to something combinatorial, but something combinatorial that's a little more tractable than Khovanov homology. The proposition is that there's some 5 braid beta whose closure, so you just glue the top to the bottom like I've shown here, is actually an unknot, and such that our knot K that we're interested in that has the same Khovanov homology as the 2,5 torus knot. So K sits inside the branch double cover of this braid closure, as a lift of the braid axis. So again, the closure of this braid beta is an unknot. So the branch double cover of S3 with branch locus the unknot is again the 3-sphere. And since this braid axis alpha has odd linking number, specifically 5, it lifts to a simple closed curve in S3. And that I claim that simple closed curve is actually supposed to be our knot. And so to prove it, we use what we know about the dynamics. The monodromy H of our fibration of the knot complement is isotopic to a pseudo-Anosov, which we checked has at least 2 boundary prongs in either of the stable and unstable foliations. And what that means is that if we fill in the puncture, it actually extends to a pseudo-Anosov map on a closed genus 2 surface. The point being that you fill in the puncture with, you just say, let's add a point there and let's make it a fixed point to the map. And then because we had at least 2 boundary prongs, you can extend both of the stable and unstable foliations across that point. So here's our punctured surface. The red and blue lines are maybe a foliation with 2 boundary prongs each, and you just sort of complete them like I've shown here. And the point is, well, we knew the fixed points before we filled in this puncture. We knew there weren't any. So now when we've reduced ourselves to looking at a closed genus 2 surface, the filled in puncture P is the only fixed point we've got. Now the next thing we use is the fact that we're in genus 2, so, it's not as special as genus 1, but it's still pretty special in that every mapping class is hyperelliptic. So there's some hyperelliptic involution. Here's an axis that meets the surface in 6 points. We rotate by 180 degrees about that axis. And we get maybe a sphere with 6 marked points, the fixed points of that involution. And every mapping class commutes with some hyperelliptic involution. So sort of a way to say that in reverse is that this genus 2 mapping class over here lifts some pseudo-Anosov map, a diffeomorphism of the 2-sphere that fixes 6 marked points. And I've drawn it here, 1, 2, 3, 4, 5 points. And I mean for the boundary to be sort of the 6 mark point, is thinking of this as a sphere rather than a disk. So the point is, if P is a fixed point, then its image under the involution, tau here, is also fixed, but there's only 1 fixed point. So P has to be one of the fixed points of the involution, as I've drawn here. And that means that it projects down to a marked point of the diffeomorphism of the 6-pointed sphere. So finally, if we take our original monodromy before filling in the puncture and we project down, we take the quotient by this hyperelliptic involution, we get a map of the disk to itself with 5 marked points. And its mapping torus is, if we just trace the marked points, sort of, as we go around the mapping torus in the circle direction, we get exactly the closure of some 5 braid. We name its braid axis alpha hat, as I've done there. And the point is that when we take the branch double cover of this mapping torus, well, we get an open book decomposition of S3 because we started with an open book decomposition of S3 and with binding the unknot, and we took the branch cover over the unknot. So again, we got the 3-sphere back. The monodromy is our original monodromy corresponding to the knot K, and K ends up being sort of the curve traced out by that fixed point P, which we identify with the braid axis. So K ends up being the binding of that open book. And like I said, since the branch double cover of the braid closure is S3, the braid closure actually has to be unknotted because we know that any non-trivial knot gives us a different 3-manifold. Okay, so now we've managed to say, we started with Khovanov homology. We took this detour through various types of Floer homology, through symplectic Floer homology and so on. And we ended up with this description in terms of braids. Okay, so what can we do about that now? Now maybe things start to get a little more elementary. So if a knot different from the 2,5 torus knot nonetheless has the same Khovanov homology, mod 2, then we know that the knot Floer homology is the same as that of T25. We know that there's some 5 braid with unknotted closure. If we take the branch double cover of that closure, then the braid axis alpha hat lifts to our knot K in the 3-sphere. So we've got this description just in terms of 5 braids. And so the idea is, well, let's think about that braid axis as a knot in the complement of the closure of beta, okay? So I drew alpha hat, the axis in blue over here. We sort of, you know, isotope things around so that this actually looks like a simple unknot, and then its complement is a solid torus. And so alpha hat looks like this. Now, when we take the branch double cover of, say, the solid torus, or well, really it's a double cover of the solid torus, it's branched over the braid axis, which we can think of as beta hat, then we get this symmetric looking picture of our knot K. This is alpha hat lifts in the branch double cover to something where, you know, we had some strands wrapping around, and then alpha hat, whatever that was, like some complicated tangle happened. And in the branch double cover, we just see two copies of that tangle sort of glued one on top of the other. And the conclusion that, you know, what this picture is telling us is that K is a so-called doubly periodic knot, and its braid axis, its axis of symmetry B is just the lift of beta hat in that branch double cover. Doubly periodic means that there's an involution of the three sphere with fixed set some unknot, which acts freely on the knot itself. Now, why do we care about that? You can maybe see the top that I'm going to apply a localization theorem. There's just a little more information we have to extract. Knots, if they're in S3, they have Khovanov homology. If we embed these knots in solid tori, then they have so-called annular Khovanov homology. Instead of being bigraded, this is a triply graded homology theory. And the extra grading just says you take some, you know, you resolve all the crossings, you get some diagram of unknots, and you record how many times those wind around the solid torus. And this winding gives you a filtration on the original Khovanov homology complex. So this is the associated graded object. There's a spectral sequence from annular Khovanov homology to the standard one. So the picture is, again, here's our knot K with the Khovanov homology of a 2,5 torus knot. It's periodic, as I've drawn here on the left. It's the branch double cover of this braid axis alpha hat in the complement of this braid with unknotted closure. And for the symmetry, there's a localization theorem and a Smith inequality that comes out of Khovanov homotopy theory. So this is sort of, this is a selling point for you know, this whole Floer homotopy program, is that you know, in the presence of symmetry, you can do things like this. You can get rank inequalities out of knowing that there are symmetries. So this is due to Stoffregen and Zhang. I should mention that Seidel and Smith proved a similar localization theorem that applies to symplectic Khovanov homology, but it's a little weaker in that instead of going from Khovanov homology to annular Khovanov homology, it just goes to regular Khovanov homology. So it doesn't, you know, it goes to the smaller object, the quotient of the periodic knot by the involution. Annular Khovanov homology, being at the E2 end of a spectral sequence, is going to be a little bigger. So this is more information that you can extract from the Khovanov homotopy type. So this was a theorem of Stoffregen and Zhang from a few years back. And it tells us that our knot K has the same Khovanov homology, or its Khovanov homology mod 2 is at least as big as the annular Khovanov homology of the quotient by this involution of in other words, of this alpha hat sitting inside the complement of beta as a knot in a solid torus rather than S3. And this is the place where we really need to use mod 2 coefficients, because Smith theory says that if you have a mod P action, you'd better work with mod P coefficients. Okay, so if K again has the same Khovanov homology mod 2 as the 2,5 torus knot, then the annular Khovanov homology of this braid axis alpha hat sitting in a solid torus, well, okay, over a field of characteristic 0, the dimension is no bigger than that, the same thing over Z mod 2. And this is known to be less than or equal to 10. Why is it less than or equal to 10? Because this is supposed to be 10 as well. I mean, one thing I've been very subtle about is that this bar means a sort of reduced version of Khovanov homology, and mod 2, the unreduced version, is twice as big. So this is 10 dimensional. If the original invariant we were looking at had dimension 5. But the point is we get this upper bound on annular Khovanov homology that's got rank at least 10. And that's, again, for this braid axis, alpha hat, sitting in the complement of that braid beta. Okay, now using some very non-trivial work in gauge theory, there's some work of Xie and Zhang using so-called annular instanton homology, which is, again, something you associate to knots in a solid torus. They proved that if you look at that grading on angular Khovanov homology that measures winding around the torus, that third grading, then the maximum grading in which it's supported is odd, and it has to be at least 5. And the reason for that is that this knot winds around the solid torus 5 times. That's where the number comes from. But there's extra structure as well. Angular Khovanov homology has an action due to Grigsby, Licata, and Verli of the Lie algebra SL2C. And the annular grading, this grading here, the thing that we just bounded, is actually the weight space grading of that SL2 action. It's the eigenvalues of the H operator. And so, the key fact from that is that you've got a sequence of rank inequalities that, it's supposed to be trapezoidal. In other words, the maximal dimension, or the dimension of the maximal grading, is less than or equal to that in the next grading below, which is less than or equal to that in the next grading below, and so on. So we've got some decreasing sequence of dimensions in these different gradings. We know the last one is at least 1 and that the grading is at least 5. And so just putting that together, even if it was as small as possible, namely 5, and all of these groups were one-dimensional, as small as possible, then, well, that's all right. But if this dimension were at least 2, then the total dimension, just by this trapezoidal rule, it would have to be bigger than 10, which we know is false. So that says that annular Khovanov homology in the top grading, corresponding to the winding around the torus, is 1. And we know, again, by work of Xie and Zhang, that this means alpha hat, this thing we're looking at here, has to actually be not just a knot in the solid torus, but the closure of a braid in the solid torus. And when we know it's the closure of a solid braid, we know it's actually a 5 braid. It's just determined by the linking number. So this is the part where instanton homology becomes really useful, is that it detects, in fact, it detects braids in the solid torus. And we really needed like this full SL2 action to get that. So alpha hat and beta hat are both braided about each other. This is, like I said, this is a really strong restriction. I mean, it's one thing to have a pair of braids and their closures are both unknots and one of them is braided about the other. But when you try and sort of undo the braid, try and just make it look like a single circle, the other one is most likely going to be too tangled up to view it as a braid. All right, so here's the summary of everything we've done, and we're approaching the end of the proof. If a knot K has the same Khovanov homology as T25, this 2,5 torus knot, and that's specifically with mod 2 coefficients, then we've got a 5 braid beta illustrated here. Its braid axis, we call that alpha hat. The closure of this braid is meant to be the unknot. And if we take the branch double cover of that unknot in S3, then this braid axis alpha hat lifts to our knot K again in S3. And if this is just a picture of what I was explaining a moment ago. If we try and sort of untangle beta hat because we know it's an unknot, so we draw it here, then alpha just becomes a braid in the complement of that. So they're both 5 braids. And Morton studied these back in the mid 80s. These are called exchangeable 5 braids when they both have unknotted closure and one of them each one is braided about the other. So for 5 braids, we know it's a product of exactly 4 specific elements of the braid group up to taking inverses. And what do those specific elements do? You pick 2 strands, say I and J, I less than J. You take the J strand and drag it all the way over the ith one. And then you take the ith strand and drag it over the ones to the right of that so that the 2 strands have switched places. And so Morton proved that anytime you have a pair of exchangeable 5 braids, each one of them has this form. And if this were an exchangeable n braid, then it would be a product of n-1 of these generators. And this is a finite problem because there are only n choose 2 of these generators. So for n equals 5, we've got 10 of these generators and we have to take a product of 4 of them. And beta and alpha are each going to be of that form. So now we do a computation in Sage, and again, using SnapP for the numerical parts, which again, I think are actually certifiably correct, but don't just take my word for it. So we just iterate through all such beta. There are 160,000. In fact, it turns out that using the fact that K is strongly quasi-positive, that it supports the standard tight contact structure on S3, we know that all of these exponents have to be +1. So it's not even 160,000. There are 10,000 braids to try. And what SNAP-P is really good at is saying, we take the closure of such a braid, we look at the branch double cover and see what happened to the braid axis in that branch double cover. It gives us a triangulation of the complement of alpha hat, and then we have to see, can it actually recognize that as a 3 manifold? And this is a doable computational problem. It has, SNAP-P has a nice database of hyperbolic manifolds with not too many tetrahedra in them. And it can't really find these among those, but what you do is you drill out some short geodesics in the complement of this whatever manifold you get, and you say, do you recognize that as a link complement? And once in a while you get lucky and it does, and then you say, okay, now I can I can use that to construct a diagram of that knot. In other words, what did alpha lift to in the branch double cover? You can actually hope to find a diagram for that. So here's the proposition. Alpha and beta are exchangeable 5 braids, and let A be the lift of alpha hat in the branch double cover of that unknotted closure of beta, which is S3. So if the braid beta is pseudo-Anosov, and A has the right Alexander polynomial, we know that it has to have this Alexander polynomial from the knot Floer homology, then A actually has to be this knot shown here. This is some terrible beast of a 60 crossing knot diagram. 5 years ago, it would have been hopeless to compute like Khovanov homology or knot Floer homology of this, but we've actually got pretty fast programs for that now. So you can actually say like, I don't know what this knot is. I don't know if it has a simpler diagram or not, but does it at least have the right invariance? And maybe it's strange, by the way, that this is the only knot that falls out of this computation, but it's nice because we only have one thing to check. So the point is, we use a program by Zoltan Szabo that's very good at computing knot Floer homology of, in this case, 60 crossing knots. It took about 2.5 seconds on my desktop computer. And it doesn't have the right knot Floer homology over the rationals. So we know that it doesn't have the right Khovanov homology mod 2. And so this program for computing, it actually does a computation mod 2, but the universal coefficient theorem lets us sort of detect some extra, it lets us detect some extra sort of free summands that don't correspond to 2 torsion. So anyway, so we had reduced the whole problem to saying if K has the Khovanov homology of the 2,5 torus knot, but isn't the 2,5 torus knot, then it had to be this one. And it isn't this one because it has the wrong knot Floer homology, so it has the wrong Khovanov homology. So this knot, coming back to the title of the talk, this is called the cinquefoil. This is a pretty poor imitation of the cinquefoil, so I call it the stinkfoil. And they're not the same knot, so that's the end of the proof. And that, that's the main theorem now. If the Khovanov homology mod 2 of a knot is the same as that of T25, then it really had to be the 2,5 torus knot. So just to wrap things up, there's a lot of machinery that went into this that other people developed, and I'm really grateful they did. But the hope is that at least, if you have a knot, of genus bigger than 1, as long as you can get to the point where there's some sort of interesting symmetry, the knot is periodic or something like that, then, and that passes through all this Floer homology, then there's actually some hope of being able to say, like, now we have Floer homotopy, we have Khovanov homotopy, and so that sort of periodicity, that symmetry really lets you say a lot more than you might have thought otherwise. So anyway, that's the end of the proof. That's all I had to say. So thank you everyone for your time and attention. This is a picture of a different cinquefoil. Anyway, and that's it. Thank you.
So, is there any question for the speaker?
Yeah, I mean, I've got 2 questions, but maybe it's twice the same question. I don't know. So,
okay.
So in your proof, you use a lot of different related technology, and especially you switch from one side to the other, going through those isomorphisms, the monster isomorphisms, and do you have any explanation, any reason to believe this is necessary? You couldn't stay in one plane without using those isomorphisms.
That's a totally fair question. I mean, for me, I guess the issue is that Khovanov homology is, it's part of this dichotomy that maybe Haggard Floer people are very familiar with, which is that, the more combinatorial something is, the harder it is to say anything at all about the geometry that it detects. And so you really have to pass to something, or at least I have to pass to some sort of Floer homology to understand anything about the geometry of the knot complement. You might say, like, to study the monodromy, is there a more direct way to do that? And I think, I mean, you're supposed to be able to read something like this directly off the knot Floer homology of the knot without going through these other isomorphisms, but that's something Paolo knows about and I don't. And I think, it might secretly involve some of these isomorphisms as well, hidden in the background.
Well, the baby case.
The baby case, what do you mean?
You don't need the isomorphism. You need ideas from the isomorphism, but not the isomorphism.
Okay. But there's still some very sort of non-trivial holomorphic curve machinery going on in the background, I imagine.
Yes, but it probably fits less than 50 pages.
All right. Well, that's, yeah, it's pretty short for anything involving holomorphic curves, I guess. So did that answer the first part then?
Yeah. So and maybe it's the same question, but your proof it goes through a lot of steps. You're using a lot of work by other people, and so it looks a bit like you've been forcing your way through this very difficult problem. And is there anything that you think are missing pieces that would allow a more direct proof if you knew, I don't know, some conjecture, more structure or more...
Well, so our original goal, which sort of covered the first half of the talk, was to prove that knot Floer homology detects the 2,5 torus knot. And we got stuck. And then we said, but wait, there's all this extra structure in Khovanov homology. Let's just, prove that instead. Or, let's prove that, write that paper and then see if we can fill it in. What we would need to get something similar about knot Floer homology is sort of a better understanding of diffeomorphisms of genus 2 surfaces. You have, you have a pseudo-Anosov map. We understand precisely what the stable foliations look like and the unstable foliations. We understand the fixed points. We can even write this map as a product of 4 right-handed Dane twists. Could that possibly be the monodromy of a knot in S3? I mean, we optimistically might say no. We just don't know how to prove it yet. But if you ask the right sort of expert in that area, then it might avoid a lot of the later stuff, in particular the use of, say, Khovanov homotopy. And it might get us the stronger result about knot Floer homology.
But maybe it could work the other way around, actually. Maybe you could use more of your technology to prove things about diffeomorphism of surfaces that experts in surface diffeomorphism can't prove. That would be nice.
Yeah, that would be really nice too. I think I sort of came into this project not knowing much of anything about, like, classical stuff about, say, pseudo-Anosov maps. And so I'm, it might well be out there and I just haven't come across it yet. And one day, one of my collaborators will tell me, oh, like, what about this construction? And then we'll say, well, that's exactly what we needed. We might be able to. And I kind of think that's the best way to prove what we really wanted about knot Floer homology, is to say something new about genus 2 diffeomorphisms just from these dynamical facts. We're just not there yet.
Yeah.
I had a question a little bit similar to the one of Patrick, which is among all these, this multitude of ingredients that you use, do you feel that there is one that plays really a key role?
Yeah, the sort of passage through periodic Floer homology and symplectic Floer cohomology, because right up until that point we couldn't say anything at all really about the monodromy of the map that might let us find and exploit some symmetry. And if we get the result about not Floer homology, that'll still be in it. That'll still be sort of an essential part. So yeah, I guess in particular this work of Lee and Taub's, I sort of don't see a way forward without it.
Okay.
But also I would say that the Khovanov homotopy stuff is, at this point, at least, just as an essential ingredient. I mean, Stephen was talking about proving the result by better understanding, diffeomorphisms of the genus 2 surface. And we're still thinking about that, but my sense is that that's quite a hard problem. We have this map of the genus 2 surface, the pseudo-Nosov map. We understand, like Stephen said, it's stable and unstable foliations, the prong structure, the singularities. But understanding the map from that or narrowing it down, I mean, there aren't that too many examples of that sort of thing in the literature. If we had some kind of upper bound on the dilatation of the pseudo-Nosov map, then it would be a reasonable problem because we could use some, techniques like train track automata to kind of enumerate the possible maps. But for now, that remains a really hard problem. So the Khovanov homotopy stuff is something we also don't really see a way of getting around. I mean, maybe, and there's also this SL2C action, which is important. And none of those things right now exist on the Floer homology side. So yeah, it's really not clear at all how to, get around that sort of thing.
Mm-hmm.
That's John Baldwin, by the way. Hi, John.
Yeah.
Collaborator. Yeah. Yeah. So I don't, there's a lot to be done, even though the sort of, we put the end of proof symbol at the, at the end of the theorem and that's it. But, the other big question is, I said like everything at the beginning requires genus 1 or less, but it also requires fiberness. Can Khovanov homology be proved to detect a knot that isn't fibered? Because now somehow you need a lot more about the geometry that isn't there. And I don't even know where to start with that. Yeah.
Okay.
Are there any more questions? Okay. Well, maybe I could ask something. It's
okay.
In this long stream of complicated stuff, I've lost a little bit the point where you use the fact that you know that the monodromy has no fixed points. Can you can you repeat it, please?
Yeah. Let me see if I can find the slide very quickly. The point was we were looking at the monodromy being hyperelliptic, so we could represent it as the branch double cover of a braid. It's here somewhere. Oh, maybe here. Yeah. All right. So because we knew there were no fixed points, we know that when we fill in the puncture on the fiber, that has to be a fixed point of the monodromy. And so we know that, we take the quotient, we remove that again to look at the knot complement, and now we have really the branch double cover of a 5 braid. If the puncture that we filled in were somewhere on the interior, then something more complicated would happen.
Maybe can I rephrase what you're saying?
Yeah.
So when we fill in the puncture, we have a map of a closed genus 2 surface. We know the closed genus 2 mapping class group is hyperelliptic. Everything commutes without involution. The fact that there's only one fixed point is what tells us that actually the map on the original surface with boundary commutes with the hyperelliptic involution. And right. So, and so it branch double covers this 5 braid. So that's the key.
I see. Okay, thank you. So if there are no more questions, we can thank Stephen again.
Thank you.